Hello, everybody. My name is Marius Causemann. I'm a PhD student here at Simula, and Pietro nicely set the stage for kind of the context of computing multiphysics problems in the brain on a cellular scale. And I'll continue with this, but we kind of shift the physics a bit, and we go from the electrophysiology to a problem that describes cellular poromechanics. And that's work that I've done on these solvers for this type of problem that I've done with my colleague Miro, who is also here in the audience. Let me begin by reminding you of the importance of osmotic forces in biological systems. So if you look at, these are white blood cells that are placed in distilled water, and as you can see, they slowly swell and then eventually burst. And that is due to osmotic forces acting. So if these cells are in distilled water, then the intracellular concentration of osmolytes will be a lot larger than the extracellular one. And the system kind of strives to equilibrating this, which can be achieved by water influx. The water flows in, the intracellular pressure rises, and these cells burst. And fortunately, our cells or our brain cells never experience this kind of an extreme osmotic shock. But generally, the same physical principles apply. And Pedro has shown this figure before. So it is kind of, it is known that the ion concentrations of, for example, potassium and calcium change across activity levels in the brain. So going from sleep and wakefulness as very normal states to more pathological states as seizure or ischemia. And as the ion concentration changes, that also means that the extracellular space or the interstitial space volume changes. As we've seen before, if the concentrations of the osmolytes change, cells will swell or shrink. And well, one cell type that is especially implicated in regulating this mechanism is the brain astrocytes. So there are various mechanisms by which they can sense kind of their state. So they can sense the swelling of their membrane, and they can also have mechanisms to sense the concentrations of certain ions in the extracellular space surrounding them or in the intracellular space. And then there are various mechanisms such as ion transporters and water channels to deal with these challenges and regulate their volume and ion concentrations. And if we want to think about how to model this, then a relatively simple model to describe fluid flow and the elastic behavior of a cell is that we consider each cell as a poroelastic medium. And in that sense, mostly the cytoskeleton of the cell, that's a scaffold of proteins that gives the cell most of its elastic properties. We consider this as the elastic scaffold of our poroelastic medium, and then there is a fluid component that is, in that case, like the interstitial fluid on the cytosol. And then on the extracellular side, we can actually do some, or consider this very similarly. So the extracellular space, the space surrounding the cells, is largely occupied by extracellular matrix. So again, these are some scaffolding proteins, and then there is a fluid component, the interstitial fluid, and kind of considering these two components, we have a poroelastic media both in the intracellular and in the extracellular space. And if we now think about put this into a mathematical model, then we can split our space into extracellular and intracellular space, omega E and omega I. And we have a membrane between them that represents, or an interface that represents the cell membrane. And then we can use the equations of linear poroelasticity, Bio's equations, to describe the displacement and the fluid flow in these domains. And then if we also want to include the exchange of fluid across the cell membrane, then what we use here is, or the idea would then be that we allow fluid flux across the membrane that is driven by the hydrostatic pressure difference across the cell membrane and an osmotic contribution. So that's this equation in the middle. And that then results in a Robin type interface condition. And in addition, we impose kind of the usual interface conditions of mass conservation, continuity of displacement, and conservation of momentum. And then there are a few challenges if we want to think or if we want to model or use this model to compute physiological phenomena on geometries as the ones that Pietro has just shown. So there is a very high level of geometrical complexity. We have to deal with large and complicated meshes. We have a high number of degrees of freedoms and need some robust and scalable solvers for that. And then secondly, also the model parameters, they differ by orders of magnitude. So for example, the permeability of the membrane LP is often much smaller than the permeability in the porous bulk medium. So I'll start by first simplifying the model a bit. So to later ensure mass conservation, we introduce an additional variable, the fluid flux, and then we rescale the system and also consider a static version as one would end up after time discretization with for example, an implicit Euler scheme. And then we end up with this slightly simplified system, which has only 4 parameters left. So there is lambda, which describes the elastic properties of the system. Then there is a rescaled permeability parameter kappa. There is alpha, which is a rescaled version of the storage coefficient of the poroelastic medium. And then we have LP, which is the permeability of the membrane separating the intracellular extracellular space. And if we want to then write down a variational form and write that down in a kind of compact matrix notation, then the linear system that we need to solve looks like this. This is kind of very similar to like a single domain poroelastic equation, but we end up with this LP with the normal trace operator in the flux equation, which describes the flow of the fluid flow across the cell membrane. If we want to think about like how can we precondition the system, the approach that we have chosen here is that we use the operator preconditioning framework, from which we know that if we find the appropriate parameter dependent norms under which the stability constants of this saddle point problems are independent from the parameters, and then use them as Rees maps for our preconditioner, then the condition number of the preconditioned system will be bounded. And then we use a relatively recent abstract framework for perturbed saddle point problems to identify these norms. And then one can get to the result that this blockwise preconditioner is robust in all 4 parameters, lambda, alpha, LP, and kappa. And if one then checks this on a very kind of simple unit square test problem, then one arrives at the results like this, where we basically just iterate over the whole parameter space and just test that the condition number stays small and bounded. So that's what you see here. Basically, all lines are relatively or quite flat, and it's in the low single-digit numbers. So this seems to work quite nicely. And then if we go further and think about how to discretize this and then actually implement this preconditioner efficiently, then what we went for here is a quite low order approximation, because we already have such a fine mesh to represent all the interfaces and cellular membranes. So we are using a Croiseau-Ravea element, a stabilized one for the displacement, a Ravea-Thomas first order element for the fluid flux, and DG0 approximation of the fluid pressure. And that then gives us a locally mass conservative scheme. And then the strategy to solve the system is using a preconditioned min-res approach, and then we want efficient and scalable solvers through Fire-Drake and PETSI. And then if we look now we have derived this preconditioner, and now what we need to do is figure out a good way to approximately solve each of these individual blocks. And already the first one poses a bit of a problem. or at least to my knowledge, there isn't really a plug-and-play solution to solve this elasticity problem in the incompressible limit, which would be if lambda is relatively large. So we restrict ourselves to the lambda small case in the following. There are ways to solve that, but we'll do it that way now. And then there is the flux problem that we need to solve, which we solve with hybridization, which I explain later. And then for the fluid pressure subproblem, we can use a standard Jacobi preconditioner. Okay, I'll briefly go over this. I'm running out of time. So the subproblem for the flux is essentially an H-diff inner problem. So that's the sum of the L2 and the H-diff norms plus a perturbation. And it's relatively well known that hybridization is a very efficient technique to solve H-diff inner problem types of system. Yeah, so there the idea is we break our space up into a discontinuous version, and then we enforce the continuity using a Lagrange multiplier. We end up with this type of saddle point problem, and then we can solve this with a Schur complement approach. And this Schur complement has characteristics that are somewhat H1-like, so they are very amenable to be solved with the classical algebraic multigrid approach, which is what we do for this system. And then we can look at iteration counts in a 3D unit cube example and see that if we now solve this with exact preconditioners, we have relatively low iteration counts and a very moderate growth with mesh refinement. And now if we use this inexact preconditioner that I've introduced before, then this still holds with the exception that we only consider small lambda because, yeah, there is the elasticity block that we cannot solve efficiently without that. I think I'll skip this. So we have a kind of nice method to derive finite element meshes from segmented electron microscopy data. And that is something that I use to generate 3 meshes of astrocytes with increasing domain size. And they go from a relatively moderate number of maybe around 80,000 cells to roughly 3.5 million cells. And now if we test the solver on these first 2 smaller ones, and again run a sweep across the parameter space, we see that it performs well in all parameter regimes. And now finally we can use all these pieces and come back to our swelling scenario. And now impose an osmotic shock of around 1 Pascal on this astrocyte and compute it over a course of 1 minute. And what you see here is that color-coded, that's intracellular pressure. So it slowly rises from the initial condition of 0 Pascal to match the osmotic challenge of 1 Pascal. And if you look closely, you also see that the geometry, it swells up, so the cells gets larger. Regarding next steps, I want to use that model in a neuroscience setting to investigate volume regulation mechanisms on astrocytes and maybe more on the mathematical and numerical. There are still a few challenges about imposing pure Dirichlet boundary conditions and the null space of that operator if the storage coefficient goes to 0. And maybe when I'm also thinking about looking into a 4-field formulation where one introduces an additional variable to deal with the incompressible limit. Thank you.
For Marius. Did you have to do any parameter tuning of AMG?
I did a few modifications that made it a bit better, but I think the classic, like the just out-of-the-box version should work quite well.
You use the same permeability coefficient inside and outside the cell. Should they be different in the real system?
Yeah, they should be. Yeah.
How much of a effect?
I think it's very difficult to get kind of actual numbers on the permeabilities in the brain. So if you look into the literature, it will range by orders of magnitude. I think it's fair to assume that maybe the contrast isn't large, so maybe something like up to a factor of 10 in the difference between the permeabilities, but I'm not certain about that.
So this